It's my great pleasure to introduce Chris Laumann, today's keynote speaker. Chris was in disguise yesterday at the Mad Hatter, where he gave a very different talk in a very different venue. Today he'll be telling us about a very different topic on efficient local classical channels. This really points to the breadth of Chris's interests. Chris got his PhD at Princeton, working with Project Sony. He was then an ICANN postdoctoral fellow at Harvard, career at University of Washington, where he was for 7 years before moving to BU. Chris works for almost half and half on topics in both traditional immense matter theory and in quantum optimization and quantification, and today's settlements.
All right. Thank you. Thanks everybody for coming. I assume you guys can hear me in the back. Okay. So yeah. So if any of you were at my talk yesterday, this is completely unrelated. So just don't bring in any preconceptions about the topic. What I want to tell you about is some recent work that I've been doing with Anusha, who's also visiting, and our student Sumner and Michael on shadow tomography. And this is it's a very self-contained little story. So, ask questions. It's not a super long talk. We just think it's nice, and hopefully it'll convince people that they should try to do it. Okay. So, great. I don't have a clicker. And also, hopefully, by the end of this, I suppose in this group, a lot of people will know what classical shadows and shadow tomography are. Probably have heard talks about it, but in process, we'll review that a little bit. So, right. So, the quantum blessing curve, right? The great power of quantum systems as they get bigger and bigger is that all these systems also, I should have put some in from the various experimental groups here, are building bigger and bigger collections of degrees of freedom that we think are remaining coherent and being put into various kinds of correlated quantum mechanical states. And that's cool. Those states live in a big Hilbert space. And the blessing of that is that means we think that quantum systems, if we can keep them coherent, might be able to do more than classical systems, whether it's for computation or sensing or whatever it is, right? But it's also a bit of a curse because Hilbert space is a big place, and it can be really hard to characterize the states that your system is actually producing or obtaining. So the old approach, or the approach to doing that, is tomography. So the goal of quantum tomography or state tomography is to characterize that state through lots of repeated measurements, build up some picture. So here's very roughly what that would look like. You have a state. You measure it in different bases. Here I've represented that by you do some unitary and then do a computational basis measurement, but you just measure it. And you need to do that many times in order to build up the exponentially many different matrix elements, if you want, which are sitting in this density matrix. Okay, so this is quite expensive as your system gets bigger. You need a lot of measurements. You've got to produce a state a lot of times. And to write down the outcomes of those measurements, you need a lot of resources. Either because you did a lot of measurements and you just got to write them down, or you start trying to put it back together into this exponentially large matrix. This naive approach does not scale well as a system gets bigger, right? So, of course, the thing is that most of the matrix elements in your naive representation of this density matrix row don't really matter, right? There's just like too much information. There's some very big system. You're interested in physical observables, correlations, string, whatever they are. You might be interested in all kinds of things, but you're not interested in everything typically, right? You don't even have time to be interested in everything. Maybe you guys do. So the thing that we're actually interested in usually is predicting physical observables. So for example, they could be low weight expectation values, like local expectation values, K body. In this talk, local will mean bodiness, not geometric locality. So I might want to be able to predict what is some observable given the state of the system. And you know, it might be interested in large classes of observables, not just one or two. Okay. So here are some examples: string operators, correlation functions, mean energy, energy variance. You might also be interested in somewhat more local quantities like the fidelity of the state you produced compared to some reference state, or the purity of the state, which is some measure of entanglement, or well, purity really, or Renyi entropies, etc. And so once you, what's the right way to put it? Constrain your ambitions, you know, a little bit compared to trying to get everything that could be reconstructed in the state. It means that you can focus attention on the things you want to know, and like how can you reconstruct those most. And that's the idea behind this classical shadow tomography, which is that once you've identified classes of observables you're actually interested in, then you can try to come up with efficient classical descriptions of the state rho, which will be able to reconstruct those classes you're interested in, but maybe not every possible detail. Okay. And there's an important point here. If you really know when you're doing your measurements exactly what you want to know, you should measure it, right? I hope that's clear. If, like many of us, you run in head first and you're like, look at this whole thing I got, I bet it does everything, I don't quite know what everything is, but I want to know, then you might say, do this, build up your shadow, and then, you know, ask the questions later once you've had time to think about it, right? So this is an important point. You know, this is useful to be able to later predict large classes of observables. But if you really know all I actually care about is the two-body correlation function, go measure the two-body correlation function. You won't do better. Okay. Okay. So anyway, this is the principle here. So let me explain to you what sort of the simplest, I think, most powerful version of shadow tomography is, which is proposed and developed in these papers. And in particular, the formalism, I think, is sort of most developed here in this last paper. Okay, so what is the idea? This is the product scheme for shadow tomography. It's very simple. You have a state produced by your favorite system. You take a set of random single body unitaries and you apply them, and then you measure in the computational basis. And then you write down, I did unitary 1 on qubit 1, unitary 2 on qubit 2, etc., up to the B unitaries and the bit string you got out. And then you repeat. So in a sense, this is kind of the obvious thing you would do. You pick unitaries and you measure, you write down what you did. Okay. One sort of important point is that you actually, the simplest case is to think of these U's as being completely far random, uniformly random. It makes some of the analysis simpler, but you don't actually have to do that. You can take them to be Clifford group elements, which is a nice discrete group, which is easier to deal with and easier to write down because it's a discrete object. Okay. So now I've written down that table. We call it the shadow table. By the way, did I say where the word shadow comes from? No? Oh, I apologize. So, you know, you have this quantum system and it has this quantum state, which is a density matrix, which is like the truth. And it's extremely complicated truth that we can't understand as poor classical mortals. And so we can only see it darkly, as on a shadow on the wall. with a polynomially reconstructed representation. Okay? Okay, good. So now you all know why it's called a shadow. Good. So how do we do that reconstruction? And here there's a beautiful sort of mathematical trick, which is the product call that I just told you defines what's called a shadow channel, which is just the expected value of the post measurements. Okay? And on the left, I've written M of rho. On the right, you might notice there's no rows. It's hiding inside that expectation value with the Born rule probability that's governing the B outcomes. Okay. And if that channel is invertible, then the protocol is homographically complete, which means that in principle, you can reconstruct the entire density matrix if you did it many times. How do you see that? Well, if it's invertible, I can apply the inverse to this upper equation and find that rho, my density matrix, is the expected value of the inverse acting on this output state. Okay. Notice the important role played by linearity, that I can move expectations through inverses. That's it. That's the key step. But from this, we now get an unbiased estimator for the density matrix. We replace this expected value by an empirical average over the samples we got. And this representation you usually should not compute, right? Because this would, again, naively be an exponentially large matrix. But this representation is how we will construct unbiased estimators for the things we do want. Why it's an important one. Okay. Uh-oh. My build is broken. Okay. So from that representation, if I want to know the mean of some observable O, I get an estimator by basically, multiplying this thing by O and taking a trace. Okay. So there it is. The only additional thing I've done is I've used the hermeticity of that channel to move the M inverse onto the O off of the sample data. Okay, so this is the sort of key formula for understanding how you do reconstruction in this kind of tomography. And it raises, well, first of all, from our derivation, this is unbiased. This is, we expect this to eventually converge for enough samples to whatever we're trying to reconstruct. But it raises a bunch of questions about how you do that and how quickly it converges. So the first is, this is clearly going to have each of the samples as an independently sampled entry. And so there's going to be statistical fluctuations on this estimator. And there will be some error, right? Which will get beat down in the usual way that errors do, as a square root of the number of samples, right? So how many samples to obtain a guarantee that our estimator is close to the true value? Okay, so that's a question that we would want to answer. We don't want it to be too big for this to be efficient. How hard, notice in order to compute this thing in the trace here, I need to be able to compute this thing in the trace here classically, it's post-processing. So how hard are these unitaries to sample and implement at the quantum stage, right? I had to do them. And how hard is it to classically compute the thing in this bracket here in post-processing? Okay. So these are kind of the three important questions for deciding whether our scheme is actually practical and efficient. Okay? And let me give you a few answers. So for this product channel, if I'm interested in reconstructing the expectation value of k-body operators, and I'll restrict technical reasons to k-body Pauli strings, so like XYZ operators, then here are the answers. So first of all, the product channel was pretty simple to implement. I only need to be able to do single body gates, right? Okay, that's okay. The sample complexity, so this is the number of samples I need to get my estimator for this O to be guaranteed to be within an error epsilon of the true value, scales as 3 to the k divided by epsilon squared. Okay, so the epsilon squared there is sort of generic. It's just, how variances go. But the 3 to the k It's telling me that there's no dependence on the size of my system. There's only a dependence on the bodiness of my Pauli operator, how local it is, the support of it, right? The storage per query, that's like, how much do I need to write down in each of those rows? I have to tell you each bit, each thing I did. And the post-processing per query actually is, okay, scales linearly with K. Here, this is very simple because it's a very local channel. You can also use Clifford tricks to make it very efficient. So this is very practical for reconstructing any local observables. Okay. So, okay, so now that's sort of review. Is it kind of clear what the picture is? Background. So, what have we done? What am I telling you about that goes beyond this or adds to this? So, what if your system has a fundamentally conserved quantity, like your atoms conserved, and you're interested in the quantum state of a system which has particles that move around, right? Then there's a problem. The single site unitaries are trivial because if I, can do things, if all I can do is an on-site gate, I can't move the atoms around. All I can do is something that gives them a phase. Say, imagine, keep in mind for the rest of this talk that I have a system of like hardcore bosons, something like that, okay? And so I put the word, I didn't put the word. I meant to put the word fundamental, okay? What do I mean by that? There's a lot of synthetic systems where we simulate systems of conserved objects, but in fact, you can break the conservation law if you want to. And then there are systems where there are actual objects that are conserved because physics has like conserved quantities like atoms and so on. And that's the case we're talking about here. Because if I can break the conservation law at the end in order to do tomography, then I might as well use the channel I just told you about. Okay. But if I can't break it, then I can't do that. Okay. Good. So this, if we think about that product channel, this unitary, the most general thing I can do, simply doesn't change measurement statistics at the outcome. So I can't possibly use it to learn everything. Okay. So the punchline, well, okay, so historically, that's true. It was observed that you could deal with this if you had global channels. They lose locality. I'll talk about it a little more in a minute. Punchline of this talk is we came up with a way to do this kind of local shadow tomography adapted to local observables in the presence of number conservation. And the channel that does it, we call the all pairs protocol. So that's what I'll explain in the next few slides. So let's back up and just sort of see why, again, why what's the trick? What's the challenge? So consider the product channel with number conservation, as I already mentioned. The on-site unitary can't change the number on site. So I can certainly reconstruct from that table of entries the occupations, the diagonal of this density matrix for two sites, right? We just look at the probability of getting a particle or not on each of these measurements, right? But I can't reconstruct anything off diagonal in this density matrix. So this channel, once I have number conservation, this protocol simply will not be able to distinguish a Bell state or a 50-50 mixture or distinguish between Bell states or anything like that. Okay. Okay. Well, if we have a global channel with number conservation, so say that there was some channel, some big unitary here that mixed everything up and actually was a totally random channel among the possible unitaries you could do with number conservation. Actually, you can reconstruct everything in principle, but such a global unitary will scramble locality, right? So you're not going to have any efficient, you won't get any benefit if you're trying to reconstruct local observables, two-body observables from it. It'll end up being exponentially hard to reconstruct from the data you've stored. Okay. Right. and I'll flag here, I thought about talking about this, like adding it as a second part to the talk, but decided not to. This is some earlier work we have on how to guarantee that bricklayer circuits like this with number conservation actually form a K-design on the Haar random group with number conservation. So for people interested in that, I'm happy to talk about it later. Okay, so, all right. So what about, like, let's take the next simple step. What about unitaries on pairs of qubits? So, of course, we can reconstruct diagonal entries. We haven't totally given up on locality, right? We can reconstruct some off-diagonal entries. So I can reconstruct anything off-diagonal associated with the first two qubits or the qubits 3 and 4, but I'm not going to be able to reconstruct anything off diagonal, say between 1 and 3. Okay. Which, note by the way, you could do without the number conservation, just from the product. So this is actually different. Okay. So what do? We do the next maybe simplest thing you could do, which is we consider sampling a random pairing and then applying a random unitary to each pair, which we can pick from a discrete set, actually, kind of like Clifford's, and then doing this final measurement in the occupation basis. So what you'd have to write down in the shadow table is which pairing you picked, which the two-body unitaries were that you did, and then the bit string that came out. Okay, that's it. Hope it's clear, not too complicated. You need to be able to do two-body gates, or you need to be able, and ideally arbitrary sort of geometrically two-body gates. If that's hard for you, you can swap things and then do two-body gates. Okay, so good. What are the properties? So it is tomographically complete, despite the sub-channels, like each pairing channel not being complete. Once I average over them like this, it becomes a complete channel, which I'll explain to you in a minute. It preserves locality and actually gives you efficient reconstruction of low weight operators, sort of physical observables. And this is actually, in some sense, the technical hard part, though I'll only sort of flash about it a little bit. We can invert this channel, like that post-processing computation is not trivial for a lot of proposals. And often there's an exponential classical post-processing requirement. And here it's totally efficient, okay? So let me, let me explain a few of these in a little more detail, and then I'll just and then I'll sort of summarize things. So how do you understand it's complete? And this heuristic way of understanding it is useful because it allows you to see how it generalizes a little bit to other cases beyond the hardcore boson case, though I won't talk about them in any detail. So what do we need to be able to do to say that this protocol is tomographically complete? It means that in principle, we should be able to construct an estimator for the mean of any operator which can act in our number conserving world. Okay, and so we can consider any globally charged neutral operator string. Okay, here plus means like raising charge, minus means lowering charge, so A dagger and A on the first and second. Z is a Z operator, etc. So a globally charged neutral operator string will have as many raising as lowering operators. Okay. How do I reconstruct that, or how can I see that I can reconstruct it from the data that I would generate in this process? It's not so hard. If I don't have multiple occupancy, right? So I have hardcore bosons, then there will exist, then there's only a raising and a lowering type operator, and there will exist a pairing, in fact, multiple pairings, which pair the pluses and minuses. Because there's as many pluses and minuses, I just pair pluses to minuses. And such pairings exist. So I pick one. And there exists some pairings such that each pair is charge neutral. And then I could just filter out my shadow table and only look at the rows in it where I happen to pick that pair. But from that, I can clearly reconstruct the expectation value of this operator. That's a horribly inefficient way to do it. It just lets me understand that this channel is complete. Okay? It's throwing out a lot of information that could help. Okay, that's okay. What it also helps us understand is how we would have to generalize this if we wanted to allow double occupancy or something like that in the states we wanted to be able to reconstruct. We will need to generalize this to some kind of all triples or all tuples. We need to have some way that we know we're going to have combinatorial objects which are always locally neutral on whatever scale we've broken up the system. Okay. Now I put this slide in specifically for John because there's a young diagram over there. And he was explaining to me his love for young diagrams yesterday while we were having coffee. So otherwise I wouldn't have hit any of you with any of these technicalities. I wouldn't say that. So how is it that we can actually analyze both the sample complexity that this channel has and do the inversion, which is that classical plate processing? Well, this channel is very symmetric, and that's the key. So it's clearly permutation symmetric, i.e., because I pick all possible pairings. If I just rearrange these, you know, I haven't changed anything about the channel. It conserves the number of identity Z, A, and A Decker operators in any operator string that I write down that it acts on. So you can see that this is how, you know, this channel decomposes in a certain way, and you can see it if you look through sort of explicitly how it works on each pairing, on each pair.
Sorry, so why don't you go from A dagger A's to products I's and B's? Those UIJs are just.
Yeah. So the short answer is this is what it does. This is if you har average.
Oh, if you har average. Okay.
Yeah. So
okay.
and that's the natural thing to do here. Yeah.
Okay,
So
then it's.
yeah. Okay. So I'd have to think about it if there's any other way to do it. But okay. So from these properties, which you can read off from how this channel acts on strings of this type, what happens, I am skipping a lot of steps, is it reduces the action of the channel to a part, which we can factor out, which leaves the A's and A daggers immobile, and that's easy to deal with, and a part which is basically a long-range random walk of the Z's. And because it's permutation symmetric, we can actually block diagonalize the channel completely in terms of irreps labeled by the Young diagrams, basically the permutation group. And everything will reduce to getting these and getting relationships that explain how the channel acts on delocalizing Z strings. So organizing the channel when it acts on these Z strings into its action in terms of swap distance. Okay.
I'm sorry, Chris.
Yeah.
The previous slide where you said you needed to discharge maker pairing, that is because of this. Because your action doesn't convert from A dagger A's. That's why you wanted everything.
No, if you try to if you think about the action of this measurement channel, even if you actually had a different ensemble that wasn't harm, you would kill any operator that was
After the har averaging.
yeah, and the channel is after the average. Right.
Because we just had a single A dagger that can a single gate can take it to other operators with net raising charge after averaging with all that.
No, I can't change whether I can't change the charge eigenvalue of an operator.
No, you can go from R to RZ, R1, 1R, pop those around in a single gate. Those after har averaging.
R is
Raising plus.
okay.
Yes.
R can go to, by a single gate, you can,
Yeah, and you can pick up Z, but all of those are average to zero.
and you do a measurement. Yeah, it kills everything. So this actually is important because it allows us, this simplifies a lot. It allows us to actually analytically invert the whole channel. Maybe I'll skip these details. All I really want to say is that the entire action of the channel is summarized by, instead of potentially exponentially many quantities, you have to invert some huge matrix to understand how to invert the channel, is summarized by this very small number of order, number of Z eigenvalues, which we can compute analytically. And the inversion comes from that. And so what that means is that the post-processing complexity is very small. So just to summarize, this all pairs channel has of order B beam splitter type gates, two body gates that conserve number, and then those single body measurements. It has, this comes from the analysis of those eigenvalues that I sort of threw at you but didn't really explain. A query complexity which scales exponentially, again, just like this was 3 to the k. It scales exponentially with the locality of the operator. It a little bit differently with the number of Z's in it versus the number of raising and lowering operators. And then has a power law growth in volume, which we believe is sort of the best you can do for sort of simple combinatorial reasons. The storage is easy. You just need to write down what you did on each run. And the post-processing actually doesn't even depend on V linearly per row. So what I mean by this V plus 4 to the NZ is there is a pre-computation step that depends on the volume of your system. But once you've written down the output of it, what you need to compute to invert the channel is just this 4 to the NZ part. So independent of volume again. Okay. So, to emphasize, none of this is exponential in volume, and we've actually got this optimized for measuring few body observables. So I just want to, I have one example sort of, I feel like with these shadow papers, people are obligated to do numerical implementations on synthetic data and show you that it constructs what you expect it to reconstruct. So let me do that for you, but it does illustrate something. So this model is a model of hardcore bosons hopping on some kind of ladder like this, with an interaction across the rungs of the ladder. Okay? And the reason we pick this model is because if this interaction is very weak, then we expect that we just get, once we pour some bosons in, some kind of Luttinger liquid of the bosons, some simple liquid of the bosons, which will have power law correlations in the A dagger A type observable correlation, right? If I make this very attractive, then I expect a boson at the top of a rung and a boson at the bottom of a rung to pair, and then those pairs can form a liquid. And thus, I get a rung Luttinger liquid or a paired Luttinger liquid, whatever. You can give it a fun name if you want. I wanted to call it a Runginger liquid, but my co-authors vetoed. So anyway, the Runginger liquid would have short-range correlations in A dagger A because I don't have Luttinger correlations in a single boson. I have it only in the paired boson. And so what you can see here is this is synthetic data from diagonalizing this system and then doing shadow topography on it, doing reconstruction, doing everything that I just described to you completely to reconstruct these correlation functions. And indeed, you see that in the blue data, well, maybe the red data first. The red data is the simple Leavener phase, where the single boson has a long range or a power law type order, which in a finite size system will sort of look like this. And the pair correlator actually is much smaller. And then in the blue data, during the rung pair phase, and the single body correlator dies very rapidly on the scale of 1 or 2 lattice sites, while the pair ordering is much stronger. Okay. And all of this is reconstructed from the 2-body all pairs process. Okay. So what am I illustrating? We can compute 4-body observables from the all pairs, or that's the tomographic completeness. Their error bars are bigger because they are bigger operators. And so the sample complexity went up, and we fixed the number of samples we took compared to between these 2 plots. Yeah, I think that's everything I wanted to say about that. Any questions? Oh, okay. So that's it. I have a short talk for you guys. To summarize, local shadow tomography is possible with fundamental number conservation. It's a concrete protocol. We think it's simple to implement. Just need to be able to do pairwise operations and couple them. And this I did emphasize a little bit, but there are a couple of other proposals for how to do tomography on systems with number conservation, kind of this spirit, which all have a hidden exponential post-processing complexity, which this does not. And so we actually think that this is really better than sort of if it can be implemented. Okay. And with that, there's some generalizations we could talk about later if you want. But with that, let me thank my collaborators, so Sumner, my graduate student, Michael, our postdoc, Anusha, who will be giving a talk tomorrow. This is her most common outfit on a daily basis.
Faculty portrait.
Yeah. All right. Thank you, everybody.
I guess we normally start with the student question, so.
Thanks for the talk. I have a question. When you're talking about building up the shadow table,
Yeah.
how do you actually choose the unitaries you use? Is there a specific set of unitaries you use?
So, okay, so that is when you talk about shadow tomography, sort of broadly, different versions of it, they all are hit your state, sample independently from some ensemble of unitaries, do a measure, repeat. So the design part you want is pick the ensemble. That's what you have to decide is, you're going to sample it multiple independent times, you have your choice of ensemble. If you pick that ensemble to be that product one that I illustrated, you get a tomographic scheme which is adapted to reconstructing local observables. If you pick it to be like a global kind of random unitary that you sample, it will be adapted to reconstructing fidelities and global quantities and be terrible at reconstructing local observables. Okay, so that's like your design space when we're thinking about constructing a tomographic protocol in this type. And here I'm telling you for this to get a local number conserving system, a shadow tomography adapted to local operators and number conserving systems, or few body operators, number conserving systems. You sample a pairing, sample pair unitaries, and then measure. Yeah.
Thanks.
Can I go back to your slide about the numerical results?
That one?
This one.
Yeah.
I'm not so sure about what the error bar here is. Your reconstruction statistical error bar, or are they
That's the-
from the theoretical point of the expected values here?
Yeah, so the these plots, good question. The blue line, the line which is connected, actually is going through points which came from the EV. This is exact optimization data. The error bars are the statistical error bars coming to the and so you see that the sort of true data is inside the error bars, sometimes above, sometimes below, right? But that's the way to read it. So,
And I don't know, but does this system has a very clear like phase transition point, and whether this tomography works also well around that?
it has a phase transition, somewhere between 0.05 and 0.5. I don't offhand know exactly where it is. Does the tomography work? Yes. I mean, we will give you a guarantee that your estimator will be with high probability within an additive error epsilon of the true value. Doesn't care if the true value came from a critical system or not.
But in this kind of critical system, the correlation difference is very large, and you have to sample in a very way such that you can have the long distance.
So the thing which is going on here, though, if you think about how the channel works or how the protocol works, I got my critical state by hook or by crook, right? And then I come in and I randomly say, let me grab sites 1 and 7, 2 and 6, 3 and 10, shuttle them next to each other, do this random unitary, some kind of beam splitter two-body gate, and then measure. So I'm directly measuring in that step the correlation between site 1 and site 7, right? And so this thing is adapted to get, it doesn't actually care about the geometric locality. It cares about the weight, the bodiness of the operator. And that's why it doesn't really matter if the correlation lengths get large or small or whatever. If the fluctuations in those observables get large, if the two-body correlator between site 0 and site 7 gets larger fluctuations, then these error the error bars will get a little bit bigger, but those are bounded. They can't be bigger than 1 because the operators have norm of order 1, right? So in the critical state, it'll get a little bit bigger, but it won't change the scaling of how this reconstructs.
You bet.
You bet.
Can you go back to the table?
Yeah.
This is considering, I guess, terabit gates, consider three-body gates running these sort of higher order all the way up to like all the alts that scrambles very quickly. Does that reduce the number of resources you need? Are there trade-offs?
Yeah, so I think your life gets harder as you make things less local. So indeed, so you can imagine an all-to-all totally number conserving random circuit, and you can formally invert that, so you can bound sample complexity and so on for various kinds of operators. It won't be very good at reconstructing local observables. It'll be better for reconstructing global fidelities and so on. It actually is not clear how to do an efficient inversion step in the post-processing once you do that. So one of the things that happens in the case without symmetry is that you can do both this local product channel, which I told you about in some detail. You can also do a global version. The global version will be useful for reconstructing fidelities and so on. But the reason you can do it efficiently is because there's a Clifford representation, and you can exploit tricks to efficiently do evolutions of that inversion step. Without that, which this doesn't have, you would be stuck with doing an exponential inversion, like literally reverse evolving your measurement state through the unitary you had picked. And if you don't have a good way to do that, then that's very hard. Going to 3-body, 4-body, if your system is hardcore, I don't think it helps you. I think it just makes things more complicated. If your system allows, say, double occupancy, then actually, if you want a tomographically complete channel, you need to go to 3-body gates and pick all possible triples. So that isn't a natural generalization. I don't foresee anybody doing that in the near future, so. We didn't pursue it too much, but it is clear that that's what you would need to do, and it wouldn't be that hard to do the additional steps of sorting out how it works. They'll get technically more complicated. Well, yeah,
So I think I wanna go back to something I've never quite understood about shadow demography.
Yeah.
Which is sort of, I think, a philosophical question, right? You have this system which is super entangled,
yeah,
right? And it feels like you're telling me at some level, I can extract any observable that I want from that entanglement without really having to reconstruct the state. So how does that not violate a no?
okay, so it's actually a good point. I even thought about putting like some interlude on this exact thing, which is how do you, right, you know, in your quantum, like intro quantum class, it's like you learn things like if I give you a Bell, if I give Alice and Bob the two parts of a Bell state, and you say, tell me which Bell state I gave you, they're kind of similar, right? But not quite. They learn something by doing independent measurements if they can talk to each other, right? So if I give Alice and Bob the two parts of one of the four Bell states, and they both just measure in Z, and then they call each other and say, I got up, and the other guy says, I got down, then they know it was one of the 0, 1 plus minus 1, 0 states, right? If you give them that again, and they do some kind of pattern mark and then a measure, they can actually learn about the phase, but they won't learn about whether it was 0, 1, 1, 0 or 0, 0, 1, 1, but they can learn about the phase and the state. So the trade-off which is happening is that you need multiple copies of the state, but then you can actually, if the outputs of the measurements can be recombined in classical post-processing, determine which states here. Is that help? So it's an important point. With only the local measurements and classical communication, you can reconstruct it given enough copies. You can make this decision about which Bell state you got. But if you only have one, you can't learn it. So that's actually the spirit behind all of this demography. Because usually you don't actually want to do or think that you're going to do like arbitrary multi-qubit gates or your measurement in order to get at particular matrix elements of the density matrix.
But still, you described to understand an embodied state, what you just described required full n-body correlators in all the pieces, right? Which is just state.
Yeah, for the two-body cake. Yeah. So
But this, I think, is this not better than that?
Well, the number of queries you need is 3 to the. And that's the number of copies.
that's the number of copies you need, or that's how it scales.
Yeah.
And then,
So it scales like both.
well, no, because the volume doesn't depend. Volume is not there.
Oh, 3 to the k.
K is the weight of the operator.
Yeah.
Not the volume. So that's
So it's much better than both.
this down here is input.
Yeah.
Right? Nothing here, even in ours, nothing's exponential in B. There is a B dependence.
But the Bell state story you just told me
Only
has
has
exponential B.
yeah, exponential into, I guess. Yeah. There's also two volume.
There is a 2-body
So I don't know if it's exponential into not scaling, but.
What is 3 to the 2 and the limit that 2 goes to the 5?
That's an excellent.
I think that means it's time to talk to Monica or Junie.
So for qubit systems, I guess there are also techniques for using these kind of local random unitaries to measure things like the entanglement of a state or the size of an operator. I'm wondering whether you can comment on whether this kind of systems.
Yeah, so. You can, in principle, use this channel to, or this protocol to measure purities and things like that. It will scale, I suspect exponentially with volume. So that's not like if you have a, well, that's even true in the cubic case, that you have exponential, if you really want to measure a purity or something to do with entanglement, you need to know a lot, right? And it doesn't come out in simple observables without doing a lot of measurements. So that I think is true here as well. It would scale in some way we haven't tried to think through, but.
But you know, or maybe for the other question, like if I want to estimate the size of an operator, like for qubits, I could do some initial random local unitaries.
I'm thinking,
And sort of like apply the operator to some random state and measure in random bases and do that. And I'm wondering if this would generalize to them.
I don't know. I don't,
Okay.
I'd be happy to talk about it more.
Sure,
but
okay,
I don't think I know
okay.
well.
Okay, yeah, that's fine.
Yeah, so if I understand correctly, so in your scheme, this inversion process can be very efficient because your protocol is like preserved locality. But it seems to require like pairwise non-local 2-qubit gates while swapping, which might be difficult to implement in experiments. So I'm wondering whether you have thought about using ensemble Hamiltonians that are based on local interactions. Therefore, you can decompose this global unitary into some product of local unitaries approximately, such the inversion becomes plausible. Also, implementation in hardware becomes more efficient.
So I haven't thought about it very hard. I think Sunwon's group has proposals that are analogous to that. And my understanding of them is that indeed, the idea there is something like I apply Hamiltonians that are more, more easily set up in whatever system you have, and then things evolve, and then I make measurements. And that's kind of the random, random Hamiltonians give you random sampling, some sense of these unitaries. My understanding is that at the end of the day with that, you have to back evolve through whatever Hamiltonian you pick.
Yeah, but if the Hamiltonian you consider to constitute this random ensembles, if that are based on local interactions, so there could be some ways to decompose approximately as a product of local unitaries, right? Based on the Robinson-like dynamics and such.
Yeah, I mean, there could be. You have to bound all the errors in that process and see that it doesn't ultimately scale singularly. So one of the things that happens in a lot of this is that you could say, oh, I'm just evolving, back evolving, whatever. But a lot of the where these numbers come from is ultimately you're inverting some operator, which has small eigenvalues, right? And you need to be able to do it stably. And so, yes, maybe there are approximately, if I gave you a random Hamiltonian and then said, even local, and then said evolve, do a measurement, and then you said, oh, I need a back evolve, of course, the exact computation is exponential. The approximate computation is whatever level of approximation you've used for your algorithms, but it may or may not be good enough because this might have singular dependence on it. And I don't know, because I haven't thought about it carefully enough, how that works. I agree, this one, I'm assuming that the thing that your system, whatever your system of interest is, that you can do pretty well is arbitrary distance two-body gates, which might mean, because numbers, usually when you have in fact, it's not just might. Normally, when you have a fundamental number conservation law, it means that the atoms move, they don't jump, right? So it really does mean that you need to be able to swap them over next to each other while they're not interacting, and then do this, whatever, beam splitter type gate on, say, neighboring pairs and make an occupation measurement. That is what this will require, for sure.
Thank you.
Yeah.
Can you explain the V to the N plus and the query complexity?
Yeah, so what's happening there is that you can kind of see it here. Very roughly, if I want to reconstruct this operator, which has two pluses, two minuses, right? If I have a pairing that I did in my table, where this plus got paired to plus, which is Z, this channel will output 0. Okay, it just knows nothing about number changing operators on the pair. Okay. Which means that you really have to ignore all of those rows. And so the v to the n plus is essentially 1 over the probability that in a pairing, all the pluses got paired to a minus. And that's that's a unfortunate scaling. I think it's probably the best you can do. I don't have a proof of that statement. I don't think there's a way to do better. I'll also point out, if you want to reconstruct a correlation function, like a two-body, like I did, here. So if I want to reconstruct the whole function, actually, every row contributes, right? Every row contributes to, say, this to that, or something. It'll contribute to some point on there. So if I'm interested in the whole function, actually, I've not lost any. If I'm interested in only like 0.0 to 0.3, then only some fraction of my measurements actually contribute. And then that's where that APM is.
Yeah, I suppose I was wondering, so you have this 3 to the k complexity, is that the amount of complexity to find a single operator or to find all of the possible k-body operators in the system? Like to predict.
This would be if I picked a particular k-body operator and I want to reconstruct it. If I want to reconstruct, so I didn't talk about it at all. If I want to reconstruct m different k-body operators, like I want to know all the expectations, then there's the overhead actually just picks up a log out. So it's 3 to the k log out. Is essentially you mostly get information about all of them as you go, and the fact that there's a little bit of correlation, like your measure doesn't actually matter that much. You only get a very slow increase. You want, yeah.
Is there an intuition to why it like doesn't scale, like there's this exponential involved, or like there's polynomial in the volume of your system, like b to the 2 for the number of two-body correlation functions? Like, is there a reason why you're able to get the information so efficiently? Like with like log m is only like a relatively small factor that you're in for measurements.
Yeah, so I get a lot in every row, right? It's not like the row just tells me 0.1 and 0.3 correlations. It tells me 0.1 and 0.3, 0.2 and 0.4, 0.5 and 0.6. It tells me correlations for every pair, right? So every row actually has order B information in it about two-body correlations, right? So it's not quite the same as saying I only on each time got information out. That's I think
Sure.
why. I think that's what you're getting at.
Yeah, I just wanted to make sure what's the exact meaning of number combination in your problem. Like, does it work particularly well for row with some number conservation symmetry, or does it work particularly well with a functional that's like with the total hardware?
Sorry, I just didn't hear the end of your question. You got quieter.
Yeah, I'm just wondering what's the exact meaning of number conservation? So which part is number?
The system.
I mean,
This-
row? Or
Rows some math. There's a system. It has atoms in it. The atoms don't just disappear. That's number conservation.
but by system, do you mean like Hamiltonian?
Hamiltonian some math. There's a system. It has atoms. Atoms don't disappear. I mean, I'm not trying to be too glib. What I really mean this, like, there are conservation laws in our universe, like varying number. Atoms don't go away, right? Not locally.
Technically,
Out of your experiments, maybe. It's important to say that the number, like the atoms are all out of the system, right? Which they obviously do in real experiments, optical lattices or whatever. So you can say, oh, the number in my system is not conserved, it's going away. That's always ignorant. You can't make superpositions that are coherent, right? You can't do measurements with, like, you just can't. You can't locally say, I'm going to put this into a superposition atom and no atom. I have to bring an atom from somewhere, and then I can do it. I can say, I can make a superposition of atom over here and atom over there.
Well, for photons, you can.
For photons, you can. So photons don't have
Everyone
one.
in atom, you have an atom laser, you put in front of it.
No, but we can debate about exactly what it means. So for superconductivity, if I break a U1, then the atom or the electron in that case, the electron pair, goes in and out of a condensate. So in a mean field description, it looks like everything's gone, but actually it's going in and out of a condensate, and microscopically, there is a number, say on the whatever, Cooper pair box or something. There's a number here and there's a number there, and the superpositions you're making have to do with fluctuations between the box and whatever it's called. So, I think it's actually like, that's why I said fundamental. You can't locally just change the number. It has to come from somewhere, right? It can come out of a condensate, which may be a sort of a response, but you shouldn't ignore that fact. So does that help?
Okay, is it true that all the observables you care about in your setting is like it commutes with the total Parker number? Is it true?
Yeah, because you can't measure anything else. It always zero.
Okay, so it's like a subset of all observables.
I think we should talk about this off.
Yeah.
Chris will be here for a while, so let's make sure.
Okay.